3.9 is on tangent line approximations, or we call it linear approximations. And we'll also look at what's called quadratic approximations. Somewhat brief section, but it's really important concept to cover for future stuff. So here's the idea. Suppose you have a curve. So you have some function that does whatever. Oops, I just erased that. It does whatever, comes up like this. Okay, so there's my function f of x. And let's say we want to look at a tangent line at a point. So right here, let's suppose we want to look at this tangent line. And so the idea is, so we come down here, here's our point A, up on the graph, or y-axis is f of a, and we want to essentially approximate that curve around that point. So you come up to the curve like this, and if you look at it, isn't the line like right close to here about what the graph is? And of course, if you zoom in, it would be a little off, and then my line, of course, goes over the top of it. But so as you come out farther here, it's getting much different, right? But right around here, the line is approximately the same as the function. So that's the idea. So what we want to do is we want to find, let's change back to white here. So find an equation of the tangent line of f of x at the point a f of a, because that's the point in question. So if we use just y minus y1, the slope-intercept form, m times x minus x1, and instead of using y, that's at a, that's f of a, and then what is the slope of that line at a point, right? You know that's f prime of a times x minus a. So if we solve for y, we get y is equal to f of a, plus f prime of a times x minus a. And that form we call the linearization of f of x. So that's equal to L of x, or the linearization of f of x. So around the point, like close to it, you get an approximation of the curve. So that's the idea. So here's an example of what you're asked. Essentially, this type of thing was really done to approximate like weird functions like cube roots or square roots or something that would be difficult to actually calculate. But you can do it, much more easily, like by hand with a line. But it has future applications too in infinite sums and things like that. So here's an example. So find L of x, the linearization of f of x near a, meaning near the given point. So f of x in this case will be the cube root. We're going to just assume it's the cube root of x. And now you have calculators and stuff, but you can just plug it in and get a value, which we'll do, but the concept is further reaching than just that. So that at, and they give you a is equal to -8. So you calculate the linearization. So L of x is f of a plus f prime of a times x minus a. And you do that calculation. So f of a is the cube root of negative 8. And then do the derivative. So it's going to be 1/3 x to the negative 2/3 x minus negative 8. Just substituting in everything. And then now we simplify. So that's equal to negative 2 plus 1/3 negative 8 to the negative 2/3 x plus 8. So this is a nice number. Don't get me wrong. Like, you know what the cube root of 8 is. But it'll show you, that you could simplify and get closer. We continue to simplify, and you get negative 2 plus 1/3. And then 8 to the 2/3 is, I suppose not obvious. Cube root of 8 is 2. 2 squared is 4. And then you flip it, and so it's 1/4. So you get 1/3 times 1/4 times x plus 8. Continue to simplify, so it's negative 2 plus 1/12 x plus 8. And you could distribute the 1/12, I suppose, but that's good enough. So what we want to do is, let's just suppose we knew this was the linearization. So we're going to use this nice simple form to approximate the cube root, because those are just fractions and stuff. Okay, so that's the idea. So use the linearization to calculate f of negative 8.1. So you know what cube root of 8 is, but like, what about 8.1? Like, that'd be tough to calculate. So we say it's approximately L of negative 8.1. So close to it, right? Close to the value, like you're going here, it's going to be almost the function value. That's the idea. Okay. So let's do L of negative 8.1. That's equal to negative 2 plus 1/12, then negative 8.1 plus 8. And I am going to use a calculator to do the rest of this stuff. Negative 2 plus 1/12, negative 0.1. And then when you add that up, you get that is equal to negative 2.008, and then it's 333. And that's exact. Cause I didn't round. I think I didn't round. I can check that. So check that. See how close it is. That's as far as I went. Let's see if I can do this quickly without, because the 1/12 might be a problem. So let's see. I did negative 2, and then 1/12. And then the 0.1, and that's negative. I'm going to multiply that and then add it. So it is repeating. Okay, so I ended up getting a repeating because of the 12 in there. All right, so now using your calculator, this is what we have now, but this is to verify the concept. Let's go ahead and calculate the cube root of negative 8.1. So that, on your calculator, you'll get negative 2.0082988. I hate when it does that. when I stop, I'm going to look 8, 8, 5, 0, 2, 5. So we can see that this is very accurate to 1, 2, 3, basically 4 decimal places. 1, 2, 3, 4 decimal places. So for most purposes, you know, kind of back in the day when this was done, that would have been pretty good. If you wanted to go, you know, you wanted to do that calculation. All right. Let's look at what's called quadratic approximation. And again, these concepts extend past other things. This goes into how to do infinite sums and get exact values if the sum continues infinitely, that kind of thing. This will be what's called a Taylor and Maclaurin approximation when you get into Calc 2. So this is next. Let's just go to another page here. This is on, when I hit the bottom of that bar down there, it does that. Okay, so quadratic approximations. Of f of x near a. So that's what we're doing. Okay, so f of x for a quadratic is approximately, I'm not doing this derivation, I'm just going to show you. It's f of a, so this is the linear approximation, and then f prime of a, x minus a, and then we say plus, it's f double prime of a over 2 times x minus a squared. And then there's a pattern to this that you would keep going, don't write this, but you keep going in this pattern and it becomes the exact value around the point. But we're just going to do quadratic for now. So we're going to, so the idea, let me draw a little picture of this. So the picture looks similar. Let's see if I can do this reasonably. So here's your x and your y. So you have your function, right? So you have a linear approximation. It's going to look like this around that point. Close enough. But then your quadratic approximation might look like this. It might go like that. And so it's better approximation around a point. Like it's better for more values. Can't really tell by the picture, but what you're kind of saying then is right in here, it's a better approximation than the line. The line is going to like come off the graph too quick, where this type of approximation might be better. So that's what's happening, you know, graphically, geometrically. Let me label a few things here before I don't like it. Okay, so there's your L of x, and then this would be your quadratic Q of x kind of thing. Around the value a, like that. Okay, so let's look at f of x doing the same thing, cube root of x, and evaluate. So you want to get f double prime. So from above, f double prime of x. So we're going back up here. Which is the derivative of, let's just copy it so you see it. Where'd it go? Here it is. Okay, so there's f prime. So we're going to take that derivative. Okay, so we'll just say d dx of that. Okay, so that derivative is negative 2/9. Subtract, and you get x to the negative 5/3. Okay, then we're going to evaluate that at x equals negative 8. And then we'll be able to like substitute back into the other form. So that's equal to -2/9, -8 to the -5/3. And I'll let you do that calculation. That's 1/144. So essentially you're adding 1/144 to that other equation to get a better approximation. So now f of -8.1 is equal to, so see what's happening here? So this right here is L of x, so which we already did that. So we already did L of x. Now we're going to add the rest of it. We're going to add this part of it, which is my quadratic approximation. So that's what I'm going to do. That's the double prime over 2 and the x minus a. So this is approximately, approximately the -2.0083 repeating, and then plus 1/144 times a half, or put a half down there, and then -0.1 squared. That's the rest of this, right? I just did that. There's your 2. And then evaluating here is, where is it? Yeah, that's your 8. You're at your point 8 minus the point 8.1. So just to be clear here, you're doing 8 minus 8.1, which is 0.1, or put in the correct negatives and stuff. So we did that back here too. I think I failed to say, oh no, I actually showed that step. Yeah, I showed that step here. So that's where you get that 0.1. So same thing here. There's your 0.1. Okay, you calculate that, and you get this is equal to the -2.0082986111111. And then, oh, that's what you do when you add that up. Oh, okay, sorry. And then the one above, so it basically give you a better approximation. So this is the from a calculator, and then you get, right? Now you're getting a little better approximation. This was 8 here. So now you're at 0.98 right here. And the rest are the same. Before, it was accurate to 1, 2, 3, 4, 4. Now it's to 5, 6 by adding that extra term. And then actually, if you keep going in this manner, and this is what's called a Taylor approximation, you'll get an even more accurate, and it actually approaches the value. So that's later. That's much later in the book. But that's why I wanted to show you this. So when you see it again, it'll look a little familiar. Okay, so if I asked you to do this, it would just be use the linearization to approximate a value. It'll be like this one above. So this is what I'd ask you to do. That's all. But just be familiar with kind of some of these concepts.